Hello friends, we started off our discussion on the fundamentals of statistics by creating rather a problem that we might face during our materials research. So that problem was you discover a specific alloy that involves rather some rare elements, and you want to know what would be the lattice parameter of this alloy. Now we have created rather previously several such alloys with different or varying composition, and we have measured the lattice parameters of such alloys. And what you have done is you have failed to rather label these alloys that you previously worked on. So all that you have is just one variable, that is the lattice parameters of these different alloys. Now the question is, would you be able to rather say what would be or what could probably be the lattice parameter of your newly developed alloy from your pre-existing knowledge? So this pre-existing knowledge is what will serve as our data. So the pre-existing knowledge that we have, that is the lattice parameters that we have measured, that will serve as our data. And from this data we want to see what could be the probability of the lattice parameter of this newly developed alloy. So since we don't have more than one variable, all the variable that we have is the lattice parameter that we have measured, so forth, henceforth. So those lattice parameters we have placed it, or rather we have arranged it on a scale that ranges from 0.15 angstrom to 0.55 angstrom. So we have placed the lattice parameter, we have found the maximum and the minimum lattice parameters that we have measured, and we have placed the different lattice parameters that we have measured that pertains to a specific alloys on these scales. And we rather introduced a bins so that we are able to group this particular distribution of the lattice parameters, and we are rather created this bins so that we can gather these different lattice parameters having their own characteristic values and place them into these bins. So what essentially bins are is each of these bins, they comprise of a specific range of lattice parameters, and when the lattice parameter that of a given alloy falls into this range, you place that lattice parameter onto this bin. And once you place that lattice parameter onto this bin, you stack it one over the other, and that yields us the histogram representation. So what is generally the population of the lattice parameter on a scale is now represented as an histogram. So histogram essentially involves, after introducing the bins, after creating a range in the lattice parameter and placing the lattice parameter into these different bins, you have arranged it in a unique manner. You have stacked the lattice parameters one over the other that are present in a given bin, and that leads to the histogram. And this histogram, what it enables us to do is visually it enables us to see which is the most populated bin. So in this case, this one is the most populated bin. So this one here is the most populated bin, and if you want to consider a range which is rather densely populated, then this would be the range that is densely populated. So this would be the range that is rather densely populated. So 0.2 to 0.4 is the range that is densely populated. So since this range is densely populated from all the numerous studies that you have done so forth, so all the history of studies that you have performed, it indicates that the range between 0.2 and 0.4 angstrom is densely populated. So what the existing data indicates is the range from 0.2 to 0.4 is densely populated, meaning most of the lattice parameters fall into this particular range. So our prior experience that we have gained by measuring the different lattice parameters of different alloys, which we refer to as abstractly or generally as data, this data offers us the information that most of the lattice parameter of this particular alloy will fall into the range of 0.2 and 0.4. So therefore there is a high probability of the newly measured alloy falling into this range as well. So that is what this histogram helps us understand. Again, we saw that there is a definite way of measuring this probability. So when I consider or I want to rather quantify the probability between these two ranges, that is 0.2 to 0.4, I have to sum all the lattice parameter between these two ranges, that is 0.2 and 0.4. Now when I want to say that what is the probability of my lattice parameter, say L, it lies between 0.2, so it should be equal to, and it should be rather greater than 0.2, this lattice parameter n, but it should also be less than or equal to 0.4. So what this probability is, you sum up all the population in each of these bins. So there are 1, 2, 3, 4 different bins. So you sum up all the population in the 4 different bins. So let us refer to that as n4, and you divide it by the entire population, that is n. So this would give us the probability of our lattice parameter, the lattice parameter of the newly developed alloy falling into this densely populated bins. So that is given by this expression here. So the probability of the lattice parameter falling into the range of 0.2 to 0.4, it is measured by summing up the population within this range and dividing it by the entire population. So this, apart from rather visually giving us an idea of which is the densely populated bins or which is the densely populated lattice parameters, the histogram also helps us quantify the probability within a specific range. Again, this range, it cuts across 4 different bins, and it is possible for us to measure also the probability of each and every bin. So you can consider measure the probability of these individual bins as well. However, we saw that these bins that enable us to build the histogram, they themselves pose an implicit limitation, because we won't be able to estimate the probability of the lattice parameter lying within these bins. So we have 2 bins and they have definite range of length of the lattice parameter, and if I want to have a range that sits in between these 2 ranges, it will not be possible for me to estimate it through the histogram. So therefore I need a different way of estimating and presenting this data, and also estimating the probability of the lattice parameter lying between these 2 bins. The range, when it's not restricted by the range that is associated with the bins, for that I need a different approach, and that approach comes by fitting a curve onto this population, and that gives us the distribution curve. So distribution curve essentially is what you have the population distribution represented in the form of the histogram. You translate that representation by fitting on a curve onto the histogram, you end up having the distribution curve. Now there are several advantages of this distribution curve, and one key advantage that we saw is it is possible for us to consider or measure the probability of a particular lattice parameter falling into a range that is not being encompassed or that is not being defined by the bins. So any range can be considered when your probability or when your population is represented by the distribution curve. Any range not confined to the ranges of the bins can be estimated. The probability of any range can be estimated when you are using a distribution curve instead of an histogram. So the probability of the lattice parameter, assuming a value of any range of lattice parameter, can be estimated by the distribution curve, not by the histogram. And in order to do so, we have to consider the select that range, and we have to consider the area under that range, and that will give us the probability. So if the probability now for any given range, for any range that is not restricted by the range of the bins, is measured by the area under the curve. Now there is a question like, how would we estimate the area under the curve unless otherwise we know what the function of the curve is? That is a valid question, because unless otherwise we know what is the function of this particular curve is, we won't be able to state or measure the area under the curve. Had we known the function of this curve, then by using appropriate integration, so supposing this is the function of the curve, by using appropriate integration and using appropriate range, say for instance R1 to R2, then I will be able to measure the area under the curve. But so far we have not introduced or defined any, rather associated any function to this curve here. We have treated this curve as it is, and all the variable that we have is just the population of the lattice parameter. So lattice parameter is only the variable. So with only one variable, it is rather difficult for us to come up with a function. So that is something we will try to address in this or towards the end of this lecture. But this is something that you need to understand, that just by the distribution curve alone, it is difficult for us to rather estimate the area unless otherwise we come up with a specific function, and this function is something that we will consider maybe after looking closely into the different features of this curve. So we will look this curve generally, gain some understanding of it, and we will try to rather develop a function for this curve that allows us to measure the area under specific ranges. Now, in order to do so, let's begin our discussion with the curve. So essentially, these curves are rather developed by fitting it onto the histogram. The histogram, it just represents the population distribution of the different lattice parameters. Now, when you consider rather the nature of the curve, this curve is rather symmetric. So when you consider with respect to this axis here, with respect to this axis, this curve is symmetric, and since it assumes or it appears to be a shape of the bell, this particular curve is referred to as the bell curve. So the name that is commonly associated with this, owing to its morphology or its shape, it is referred to as the bell curve. And a more technical name, it is referred to as, more technically, it is referred to as the Gaussian curve. And there is also and the other name for this is also it is normal curve. Okay, so this curve, owing to its shape, we refer to it as bell curve, and the other names that is attributed or how these curves are referred to as is the Gaussian or the normal distribution curve. And again, this is a distribution curve because it essentially talks about the population distribution. So this curve, the foundation of this curve is the population distribution that histogram gives us. So therefore, this curve is the nothing but the distribution curve. Now, when you consider this curve, there is a huge significance associated with this curve. Meaning, this curve is apart from materials research, or even since we are motivated by materials research and we started off with an application or a condition or a case wherein the material aspect is involved, this type of curve is observed in numerous places, rather in wide statistical application, in wide range of statistic data that you collect. When you rather plot the distribution of this data, you will end up observing similar type of these curves. So what is so significant about this curve is, you have, when you look into this curve, what you essentially have is, you have a low population and a high population range. You have, in the distribution of the population, you have a low population distribution and a high population distribution. And when compared to this low and high population distribution, you also have an average population distribution. So just when you compare the distribution of the population, you have high, low, and that is in between these high and low, you have the average distribution or average population. So you have a densely populated area, you have least densely populated area, and you have the average populated area. Now when you consider the population of, or when you consider the amount of the low and or least populated area and the highly populated area when compared to the average populated area, you notice that the average populated area is quite high when compared to the least and the highly populated area. So let me repeat, whatever may be the range, whatever may be it you are measuring. So in this case, we have measured lattice parameter. It could be anything. Let us say we are measuring atomic weights of different elements, you are measuring mass numbers of different elements, you are measuring several different things. But what you observe is, it is possible for us, from the range of output that we get, it is possible for us to categorize certain areas as densely populated, certain areas as least populated. And when you consider in addition to that, it is possible for us from the values themselves to refer to that as these values are rather lower and these values are rather the highest. So in this case, we have considered the lattice parameters, and it is possible for us to have refer to few lattice parameters as the least lattice parameters and few parameters as the highest lattice parameters. So we have a range of lattice parameters, and some of these parameters can be least and some of these parameters can be highest, and when compared to these two, some of these can be average. And as expected, so this least, highest and average, they come principally from the magnitude of these lattice parameters. So they do not have to do anything with the population. Just when you compare the measurement of these different lattice parameters, some are in the highest range, some are in the lowest range, and some are at the average. And now when you compare the population distribution, the amount of alloys assuming least, assuming highest, and assuming average, you will notice that the alloys assuming least will be smaller, alloys assuming highest lattice parameter will be smaller, but alloys assuming average will be large. So as is often the case, the definition of least, highest and average comes from the lattice parameter. and the population itself will will be rather distributed in such a way that the average is as the most population. So as we see in our real life, so apart from the top scorers and those who unfortunately fail sometimes, the ones in the middle are they occupy the most of the population. In the same way, we also observe in the physical world, like in this case of our example of the lattice parameter. So what it reflects is this type of representation reflects most of the physical system that we see in real life. So this representation, which indicates that it is the average that is often of the highest population. So it is the people who rather gain average marks in a given classroom. It is not the highest, it is not the lowest, but it's the people who gain the average mark, they are of the highest population. So that is rather indicated. So that is something that is often we observe in a given classroom, that is also rather indicated in this curve here. So that is the significance of this curve. When you get rid of the specific values of the lattice parameter, so in this case it is lattice parameter. Now if you want to consider as a physical examples the mark obtained by the the students in a given classroom, if you replace the specific marks with average, least and the highest, you would notice that the person gaining or getting the least mark, mostly the person getting the least mark will be smaller, or the population of students getting the least mark would be lower, the population of students getting the highest mark will be lower, and most of them would have gained or got the average mark, secured the average mark. So in a wide range of physical system and also in real life condition, we observe such distribution, and that's the reason why we refer to it as the normal distribution. So normally you observe the distribution wherein it is, so in this case it is the lattice parameter, in the other case that we have considered is the mark scored. So it is often the average that assumes the most population. It is often the average that is rather densely populated. So that is a key significance of this particular curve, this Gaussian curve or this bell curve. Once you are able to understand the aspects of this distribution curve, this particular Gaussian curve or the bell curve, you will be able to understand the statistics, the population associated with most of the real life situation, be it in materials research or be it in any setup. Okay, so this significance of this particular distribution curve, that is the Gaussian curve or the bell curve, lies in capturing the densely populated average. So often we see that average is densely populated, and this is rather captured by this particular distribution curve, which we refer to as the Gaussian curve. Now, it is not always necessary that we need like significant amount of data. We need a huge data set in order to come up with this curve. Even relatively limited data will also help us construct this curve. Again, the key term here is relatively. So there are some functions, for if we have to rather fit that particular function, if we have to arrive that particular function, we need huge amount of data points, we need huge amount of the population distribution. However, in order to fit this particular curve, when compared to other curves or other functions, the data that is required for this is rather relatively low. So that is rather one advantage of this particular distribution curve. But we should also be careful that in the data analysis, in data science, it is often more data will often give you more accurate results. So more the data, the more accurate your results will be. However, the trend of the curve, particularly in this case the trend of the Gaussian curve, can rather be arrived at with relatively less number of data as well. When compared to other distribution curves, which we will look in a few minutes, when compared to those distribution curves, the trend of this curve can rather be arrived at using relatively limited number of data points or population. Now, when you consider this particular curve here, this particular distribution curve, which we have referred to as the normal distribution curve, which we often, apart from the material research, which we have now established to be, or quite established to be found in a wide range of real life applications as well. This particular curve is rather characterized by, or it's rather described by two parameters, that is mean and standard deviation. So mean and standard deviation are the two parameters that rather is used to describe the nature of this curve here, mean and the standard deviation. Now the mean or the average, so in the context of this curve we refer to as the mean. This mean is nothing but the sum of all the values that we have measured. So in this case we have measured the lattice parameter, so we sum all these lattice parameter up. So Li is the lattice parameter of one alloy, and this we have considered n alloy, so we have sum up all the lattice parameter and then we divide it by the total number of alloys that we have considered. So Li is the lattice parameter of alloy I, and so we sum it up from ranging from first alloy to nth alloy, and then we divide it by n. So this gives us the mean of this distribution curve, of this normal distribution curve or the Gaussian distribution curve. What this means, so numerically we are able to understand what this mean is. The mean is the average of the entire lattice parameter that we have measured. So that is what numerically the mean is. Now when you relate it to the distribution curve, we notice that this distribution curve is rather positioned at this mean. This distribution curve is positioned at this mean. So numerically, mean is the average of all the lattice parameters, that values that we have measured. But when you consider graphically, the bell curve or the Gaussian distribution curve is rather positioned at a specific point, and that point is the mean. Now, while mean talks about the position of this particular normal distribution curve or the Gaussian distribution curve, what the standard deviation talks about is what is the spread of this particular curve. So the mean talks about its position, the standard deviation talks about its width or its spread, how much as this particular distribution curve is, rather how much it spreads. So that is rather quantified by the standard deviation. This mu that we have estimated, or rather this mean that we have estimated by considering the sum of all the lattice parameters. So sum of all the lattice parameters. So what we are doing is we have considered a definite population of lattice parameters of Li, and we have summed all these lattice parameter, and this lattice parameter, when you consider the population of it, is n. So we have summed up all the individual lattice parameters and divided it by n. So the population size here is n, and each of these points in the population, it represents the lattice parameter. So essentially this mean we get from the population, so therefore it is often referred to as the population mean. So this is something we need to understand. What a distribution curve gives us is a population mean. The reason we call this as population mean, because we have a definite population of size n, and in that definite population of size n, each of the member of this population, they have their own lattice parameter. So each members of this population is an alloy, and they have their own lattice parameter size, and the mean we have estimated by considering the size of individual size, summing it all up and dividing it by the entire size of the population. So since it is dependent on the population, the size of the population, we refer to it as the population mean. And now, so this population mean, it is rather represented by the symbol mu. So this mean that you have calculated, this is the population mean that you have calculated, it is represented by mu. The reason we need to introduce this term population, we need to qualify the mean as population mean, because this comes from the distribution curve, and this comes from the distribution curve again comes from the histogram representation, which is nothing but, which is based on, or which is histogram representation is nothing but the distribution of the population in different bins. So therefore this entire CAS estimation, since it is based on, or it is rather restricted to a given population, we refer to this as the population mean. Now we want to understand what is the spread of this curve. So this curve that is based on the population, it is rather characterized by two parameters. One is the mean and other is the standard deviation. Mean talks about the position of this curve, and we need to understand what is the spread of this curve. In order to do that, we need to use a specific expression, and the spread is rather understood by considering taking the ratio of x, or the individual lattice parameters, with respect to that of the mean, the whole square, divided by n. So what essentially you are doing is you are considering the sum of all difference between the lattice parameter, the individual lattice parameter and their mean. So you are considering the sum of all the difference between individual lattice parameters and their mean. So for instance, if I want to consider this lattice parameter here and this is my mean. So let me make it even more clearer. So this lattice parameter here and this here is my mean. Now this difference will give me the spread of my curve. So this is the lattice parameter of the alloy 1 and this is the mean, so mu. When I consider the difference between these two, this will give me the spread. Now the reason why we need to consider the square is because this will give me a negative value, whereas this difference here would give me a positive value. So therefore, so when I consider the nth lattice parameter n, then this difference would give me a positive value. So therefore these two will cancel out each other. The positive, the negative and the positive value will cancel out each other. So therefore we need to have a square term here. So the square term avoids the cancellation between the negative spread and the positive spread. And we are considering this spread. So we have just in this illustration I've just shown the first and the last lattice parameter that we have measured. So what we are doing is, instead of considering the first and the last, we are considering each and every lattice parameter and subtracting it from the mean, thereby considering how much far it is from the mean. So when I consider the difference between all these lattice parameters from that of the mean, then I will be able to state how far it is from the mean. So this value here, this difference helps me understand how far is the lattice parameter 1 from the mean, and this will help me understand how far is the last lattice parameter from the mean. So this we are repeating for all the available lattice parameters, and we are taking the square of it so that to avoid the cancellation of negative with the positive difference, and then we are taking the average of it with respect to all the entire population, and this is what we refer to as the variance. So what we are measuring through this formula, so this is summation of the difference between the lattice parameter of individual alloys with respect to the mean, squaring the term and taking the average of it. This is what we refer to as the variance. Now even though this variance, it captures the how far each of these points are away from the mean, since we are squaring it, what essentially we have captured is the square of the distance. So even though the difference between the lattice parameter of one alloy with that of the mean, it estimates its distance, since we are squaring it, we are essentially calculating the square of the distance between the mean and the lattice parameter of an alloy. So just the difference alone will give us the distance between the mean and a given lattice parameter. However, since we have to avoid the cancellation of the negative and the positive distances, we have squared it. So ultimately the output we get from this expression is the square of the distance, and that is what we refer to as the variance. And now when I want to calculate the standard deviation from that of the variance, then it will be the square root of the variance. So what essentially we have is, we have a mean, that is nothing but average of all the different lattice parameters that we have measured. That is what we refer to as the mean, and this mean is a population mean because we are just calculating it from the population. So the given population of size n, and in that population of size n we have n different lattice parameters, and from that we are calculating the mean, and that is referred to as the population mean. And this population mean gives us an idea about where the curve is rather positioned. Now we want to also know, so once we have fixed the point for the curve, we want to know how spread the normal distribution curve is. So in order to do that, we are considering the difference between mean and the individual lattice parameters. And when we consider the difference between the mean and the individual lattice parameters, in a scale it gives us the distance between the mean and the other populated area. So it gives me the distance between the mean and the lattice parameters of other alloys. However, since we have negative distances and positive distances, in order to avoid the cancellation of negative distances by the positive distances, we introduce the square term. So when I introduce the square term, what essentially it becomes is, we are then estimating the square of the distance between the mean and the individual alloy lattice parameters. So in order to rather move away from the square term and get a value for the exact distance between the mean and the other lattice parameter, we take the square root, and that is what we refer to as the standard deviation. So variance is rather the square of the distance between the mean and the individual lattice parameter, whereas the standard deviation, when you take the square root, is the exact representation of the distance between the mean and the lattice parameters that we have, that we get from the population of size n. So using the combination of the mean and the standard deviation, we will be able to rather both position a given a specific bell curve, and also we will be able to discuss the trend, the spread of this particular bell curve. So when we are talking about the distribution curve, there are two parameters, that is the population mean and the population standard deviation. Again, this also is estimated from a population of size n, so therefore this is referred to as the population standard deviation. So from both these, it is possible, from the population mean and the population standard deviation, it is possible for us to estimate, rather to say the configuration of our distribution curve. Mean, the position, and the standard deviation would give us the spread of the curve. So now when we write down the expression for the population mean and standard deviation, this expression would be the summation of I 1 to n Li divided by n, and for the standard deviation it would be the square root of the summation of I 1 to n, the difference between the lattice parameter and the mean square divided by n. So this is population mean and standard deviation. Now often it will not be possible for us to measure the lattice parameter of all the alloys that are present. Often it will be the case that the n is different for different experimental conditions. So in some cases, the n that we have with us, the subjective n, will be less than the one that we theoretically consider, or it can also at times be greater than the n that we theoretically consider. But since often theoretically we assume the n that is rather dense, or the n that is an ideal one with most population, the n that is available to us is rather often less when compared to the ideal number of population. So let me repeat. So when you consider the population, so there is an ideal number of population, the ideal population size that is required to arrive at this curve. Often in real life situation, we will not have that amount of data set to arrive at such curves. Even though we are able to arrive at such curves, the number of data points that we have with us will not be as high as what is expected or what is ideal. So this, when you describe the population mean and population standard deviation, the n described here is rather an ideal size of the population. Okay, so even though we started off with a case, we have been assuming that the n that we have is rather suitable for arriving at this particular distribution curve and accurately estimating the mean and the standard deviation. But in case of real life situation, the n that we have, so if I say nRL, this n in the real life situation is often less than that of the n that is ideal. So in that case, we need to have the whatever mean and whatever feature that we estimate for this curve, whatever the parameters that describes the curve that comes from the real life population, it needs to have a different name associated with it, and that name is referred to as the expected mean and standard deviation. So the population mean and standard deviation, it comes when the population that you have is of an ideal size, and very rarely we will have a population of an ideal size, and often the population that is accessible to us will be much lower than the ideal population. So in that case, even in that case, say for instance in this in the ideal case we need 100 a population size of 100 lattice parameters. Now supposing you have a population size of 50 lattice parameter, even in this case it is possible for us to sum up all the available lattice parameter wherein the I ranges from 1 to 50 and divided by 50, and this will give us a mean. And this mean will not be referred to as the population mean, but it will be referred to as the expected mean. So when the mean is rather estimated from a population that is not rather ideal, then in that case we refer to the mean that we estimate as the expected mean. And in most cases it is possible that the expected mean is close to that of the population mean. Particularly when the population size keeps on increasing, the expected mean will get closer and closer to the population mean. And the same goes for the expected standard deviation. In this case, when you replace the n with 50 with a non-ideal size of the population, you will end up having an expected, you will end up estimating an expected standard deviation, and this expected standard deviation will translate to that of the population standard deviation when the size of the population is when it increases. So the expected standard deviation and the expected mean, they are the means and the standard deviation that we usually calculate in a practical instance when the population is not as ideal. So what essentially we have is, we have now made the difference between population mean and standard deviation to that of the expected mean and the standard deviation. Since even when the population is not as high as ideal, since we are able to estimate the expected mean and expected standard deviation, using the expected mean and the expected standard deviation, we will be able to construct a curve of this sort. And that is the reason why we stated that even with the limited data set, relatively limited data, we will be able to come up with such a curve. Again, even when you don't have a size of the population that is ideal, with the existing population alone, we will be able to calculate the mean and the standard deviation. We have seen the formula for it. Now those are referred to as the expected mean and the expected standard deviation. Using this expected mean and the expected standard deviation, you will be able to come up with a curve like this, and this curve is rather, it arrives from the relatively limited data set, and therefore there is one key advantage of the normal or the Gaussian distribution. So I hope you are able to understand the difference between the population mean and standard deviation and this expected mean and standard deviation. Often we will be operating in the range of expected mean and standard deviation, and the more the value and the value of or the size of the population as it increases, we will get closer and closer to the population. The expected values will be closer and closer to the population mean and the standard deviation. So this is one key aspect that we need to consider when we are rather discussing this distribution curves on these histograms. The accuracy of it, the closeness to the standard, the population standard deviation, and the closeness to the population mean and standard deviation. This will come from, or this is based on the population or the size n that we have. When the size n that we have increases, the population mean and standard deviation will be close to that of the expected mean and standard deviation. When the population size that you are considered, when it keeps on increasing, the bridge or the gap between these two will keep on decreasing. So the expected mean and the standard deviation will get closer and closer to that of the population mean and the standard deviation when the population that you are considering increases. So of course, in data analysis, that is the reason why, even though we are rather in this instance we are talking about the Gaussian distribution or the normal distribution curve, usually in data analysis large amount of data is preferred. So that's the reason whenever you have a discussion with a data scientist, they often question you about what is the size of the data set you have. So often the greater the size of your data, the greater would be the accuracy of the model that you develop, the greater would be the, so in this case the model is nothing but the curve that you develop, so the greater would be the accuracy of the curve that you develop when you have densely populated data set. Now in addition to that, within the context of histogram and this distribution curve that you get out of it, other factor that determines the accuracy is rather the bin size. Now when your bin size is quite small, if it is very small and the range of the bin size is small, what cannot be done is it will not be possible for us to rather separate the lattice parameters into different bins. So when it becomes rather difficult for us to separate the lattice parameters into different bins, it becomes quite difficult for us to arrange it in the form of a histogram. And when you are not able to arrange it in the form of histograms, arriving at or fitting a curve over it will become quite difficult. So accuracy, in addition to that of the population and the number of data points we have, which is common for all data analysis, apart from that, for histogram, in the context of histogram, the accuracy of the fitting that you have, it depends on the size of the bins, and they are so small it is difficult for us to rather separate the lattice parameters into these different bins, and most of the bins will be empty. If the bin size is quite large, like what we see here, then it becomes it turns out to be meaningless. Instead of having a function, what you would then have is, or instead of having a distribution, then what you would have is a straight line. So you will be rather making it categorical as 1 or 2. So even the size of the bins play a vital role when you are translating a population distribution to a distribution curve. The size of the bin plays a vital role. When you want to translate a population distribution on a scale to histogram and ultimately to a distribution curve, then size of the bin plays a vital role. Now, before winding this lecture up, let us just get an idea of what are the other distribution curves that are possible. So when you have a distribution, we consider the same experiment, we consider the same problem, and now what we have is a population of different lattice parameters, and now these lattice parameters in a scale are arranged in this manner. The population of this lattice parameter that we have measured so forth is rather arranged in the scale in this manner, and when you fit an histogram to it, the distribution of it looks something like this. So instead of having a normal distribution wherein the least parameter is rather less populated and the highest lattice parameter is less populated and the average assumes the most population, instead of assuming such normal distribution, we have such a unique distribution wherein the least lattice parameters, the number of alloys assuming the least lattice parameter is quite huge when compared to the other lattice parameters. So you get a distribution like this. To relate it to the example that we have considered, assuming that supposing you take a very difficult class, and in that class the question paper and the topic that is being taught is difficult and the question paper is also difficult. In those classes, the number of students getting the least marks will be highest. So that is something that we could relate to. And in the same way, in this case, in these alloys, the alloys with the least parameters are quite large when compared to the alloys with average and high lattice parameters, and you get a distribution of this sort. And when you fit the curve over it, and we get an exponential curve, and that is the nature of this exponential curve. And now we also have other sort of distributions wherein the population is not rather focused on the central region, the dense population is not focused on the average, but it is rather shifted from the average. It is rather, it occupies a specific position, and this position can vary depending on the population that we consider. So in such a case, okay, it is not that the average of the lattice parameter is densely populated, it is rather away from the average, and correspondingly your distribution is skewed. So you get an histogram of this sort, and such a distribution, the distribution of the curve that you get from such a distribution, we refer to it as the gamma distribution. So ultimately what we have seen is, apart from the normal distribution, there is also the possibility of the exponential distribution and the gamma distribution. So even though normal distribution is what we often observe, mostly observe in the real life situations, when you consider research activities, there is always some characteristic distribution that we observe, and there is rather a viable reason to why we observe such distribution. So when you want to describe such distribution, we have two other distributions that are possible. One is the exponential distribution, the other is the gamma distribution. So these are certain distribution that we might come across, or we would come across while we are involved in the materials research. So with this, I would like to wind today's lecture up, and in the subsequent lecture we will try to translate this distribution into rather a functions, because at the end of this, or at the beginning of this lecture, we saw that when you have a distribution, to find the probability you need to have an area, and in order to find an area of a specific section of a curve, we need to know the function of that curve, and that function will be possible when you are able to translate this distribution to a function that we will see in the subsequent lecture. Goodbye.